Thank you for joining. Not too loud. Okay. Thank you for joining me. And I did change a little bit the schedule this week because I had another session. But we will, next week we will come back to the regular time, Thursday 11. But thank you for accommodating to the new day and new time for this week. Okay, that's what we have. We do have a lesson 10, and this is the end of chapter 5. We will talk about the fundamental theorem of calculus, total change, of course, and the average value. We will try to compute these things. Okay, that means let's just solve a few problems. Okay, I did check the discussion board, and I think I will solve a similar problems that was on the discussion board. Okay, so let's see what we have. Oh, too fast. That's what we have. First of all, let me switch off the camera. Okay, now it's better. Okay, that means the fundamental theorem of calculus, as covered before, is defined, and we can see this, is defined this way. That means if the f prime, if the derivative is the continuous function from a to b, then the definite integral from a to b of that f prime of x dx is equal to f of b minus f of a. That means it's just the difference of the values of at the endpoints of the total change function. That means using different words, we can say the definite integral of the derivative of the function gives the total change in the function. That means this is the total change. Like we will see later, but it's like just the difference. If I would like to have the length of an interval between like 2 and 7, I will subtract 7 from 2 is 5. That means it's kind of like this idea, but we're playing with the definite integral, the areas under the curve. Okay? That means one more time we have to remember just the difference of the total change function at the endpoints. And we have some example. You can pause the video and check this example later. And I also have another things that we will need for today. Let's see this. That means this is the total change and the marginal cost. That we have to understand a few things. C at Q, it's a total function, total cost of producing the Q items. Right? C at 0 is the cost of producing the 0 units. And it's typically the fixed, we call it fixed cost. Because it's not always 0, we do have some cost at the beginning, at front. And C prime at Q is the marginal cost. It's the rate of change of the cost function with respect to the quantity. Okay, and now definite integral of the marginal cost will give me the total change in the cost, right? The total change in the function. That's the main thing. How we can like look at the integral. That means definite integral from a to b of c prime q dq, which is the marginal cost, is defined again as a difference. The total change in the cost function between a and b, which means c at b minus c at a. We have to just find the difference of the endpoints, of the values of the endpoints. That means one more time, the integral gives the amount it costs to increase the production from unit A to unit B. And again, we have another definite integral from 0 to B of the marginal cost, C prime Q dQ, and it's equal to C at B. Okay. I can theoretically say, following my fundamental theorem of calculus, I can put C at 0, but we're assuming that this is 0 and at this point. Okay, not always, but at this point. That means this is the total variable cost of producing B units, which graphically this will represent, this is the definite integral, and we know the definite integral represents the area under the curve, under the marginal cost in this case, between 0 and B. And this will be the total increase in cost between producing a 0 and producing a B units. Okay? And if I would like to, that means we can see I have that fixed cost C at 0. That means this will be the total cost of producing B units. Not always this is 0, but we may add sometimes C at 0, which of course is the cost of producing 0 units. Okay, that means this again, that's, I can maybe box this, that's the fundamental theorem of calculus, and it's important to remember and apply this at the right moment in this week. And okay, that means that's almost everything. I mean, the theoretical part. Of course, I always go really like, I have really broad review of this because I would like to focus on applications. That means let's start. Let's see if we can solve all of my questions. Question number 1. If the marginal cost function C prime Q, it's measured in dollars per ton, then Q gives the quantity in tons. What are the units of measurement of the definite integral from 800 to 900 C prime Q dq? And what does this integral represent? That means we can write down that this integral, okay, from 800 units to 900 units of the marginal cost. Okay. Of course, this is that means we will we integrating the rate, right? That means we integrating a rate, which rate is, we actually have this dollars per tons, okay? And we multiplying by tons, the quantity, right? Tons. That means we can simplify, and the whole integral, of course, will give me the total change of the function. That means the original unit, which is simply dollars. Okay, that means the integral represents the amount under the curve. We know that, but this is dollars. That means the whole integral represents the cost. We can see dollars. Okay, that means this is cost of increasing production from 800 to 900. Cost of increasing production. Okay, that means make sure that you understand from 800 tons, because Q is in tons, to 900 tons. Okay, yeah, and of course dollars. I mean, overall, I don't want to point one thing. And that means that's the meaning of the definite integral. Always we think this is the total change of the original function. Okay, let's see. Next question. The marginal cost of drilling an oil well depends on the depth at which you are drilling. Drilling becomes more expensive per meter as you dig deeper into the earth. The fixed costs are 1 million, and I don't know if I will pronounce this correctly, that's the currency of the Saudi Arabia, riyals, I'm assuming that that's good. We can say anything, we can say dollars, which actually is a lot, but okay, 1 million riyals, and if X is the depth in meters, the marginal cost is defined like this, and the unit, it's riyals, the currency per meter, the money per meter, of course. One more time, marginal cost is C prime of X, 4,000 plus 10X. Now the question is, find the total cost, okay, total cost, the total change in the function, that's today's topic, of drilling a 500-meter well. Okay, that means I'm assuming that the total cost, it's simply an integral from 0 to 500, because it's the total cost of drilling 500 meters well. And we have to integrate the marginal cost. Yeah. Then we get the total change, the total cost in this case. Okay. And from indefinite integral from 0 to 500, and I have my function 4,000 plus 10x. Okay, and how can we calculate a definite integral? We remember from the previous week, or even from this one, it's simply a area under the curve. Okay, that means I can put c prime of x because that's my function. I will draw this function 4,000 plus 10x. It's just the linear function. 4,000 is the y-intercept, yes, the vertical intercept, and the line has slope 10. That means I'm assuming something like that. 4,000 and 10. Okay, like 10 could be a little bit steeper, but I will just do for now like that. And now I'm interested at the area under the curve from 0 to 500. Okay, that means it's nice shape, I think, because all of the sides are straight lines. We can definitely approximate. Let me do a little bit higher because we will need this value too. Okay, that we have to find the area of this rectangle and the area of this triangle. Okay, that means the area of the rectangle is base times height, and the base, my units are totally off, but it's okay, because this is, can you see, this is 500 and this is 4,000. I think should be much, much higher. But okay, we have the good, correct labels. Okay, that means one more time, base times height, 500 times 4,000, which this will give me 5 times 4, it's 20, and we can count zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That means I did get 2 millions. Okay, of course, it's big numbers. And now I have to find the area of this triangle, which the area of the triangle is 1/2 times the base. Base is the same like for the rectangle, 5,000. And I have to find that height. Do you think you can tell me what is this height, that distance? I know that up to this point is 4,000. That means I have to find this value and then I will subtract 4,000 because I'm not counting this 4,000. Okay, 500. This point, this one, is the value of that line at 500. That means I can take the line 4,000 plus 10 times 500, because this will be the value of the function. I can maybe say this way. Okay? 4,000 plus 10 times 500. That means this is 5,000, 4,000, 9. That means this is 9,000. Okay? And if this is 9,000, the distance between 4 and 9, of course, is 5. That means this is 5,000. And I will multiply by this. That means what we have, 5 times 5 is 25. And 1, 2, 3, 4, 5 zeros. And we have to divide by 2 still. That means dividing 250, I can say, by 5. Let me write down here. This will be the rectangle. Okay, and this is the triangle. 5,000. Okay. The rectangle, we've got 2 millions. This one is, if I divide 250 by 2, is 125. And I think I'm losing 1 0, 1, 2, 3, 4. 1, 2, 3, 4. Of course, I'm trying to do without, 225. Something is wrong. The zero should, the comma should be here. Or maybe I am wrong. If you can use, I don't want to miss any zeros. I have 500, 1, 2, and 3. 1, 2, 3, 4, 5. 1, 2, 3, 4. No, I think, do you think this is correct? Can you multiply? I'm just trying to, 5,000 times 500 dividing by 2. Do you have calculator somewhere? I did my work before and I actually got one extra. Oh no, this is correct. Okay, that's what I was looking at. Yeah, it is correct. For some reason I thought that it's 120. It's 1,250,000. Okay, because this is in millions and I was expecting this one. Okay, that means now we can just simply add together. That we can add this, and this will be 3 millions because 1 plus 2 is 3, and 250,000. Yeah. Of course, for these big numbers, I mean, I'm always trying to calculate everything without the calculator because I was always taught that calculator is not really available for me. That's what actually we have to do on the final and the midterm, right? We're not really using the calculators. But of course, the numbers are a little bit more friendly. Okay, that we do have, but hang on, we have to remember, let me actually put the cost. This integral represents the cost. In order to find the total cost, I really have to add the fixed cost too. I'm trying to do total cost will be the fixed cost plus the total variable cost, because this is like a variable cost, plus total variable cost. That's implicit. Is that the thing is that we have to just add whatever cost we had at the beginning. That we did have 1 million, which is 6 zeros, and plus my value, 3,250,000. Okay, and the final answer is of course 4,250,000. And of course, this is dollars. Actually, not dollars, rivals. Can I say this? The units of the currency of the Saudi Arabia. I can put this. Okay. That means the main thing is to remember to add the total cost to the variable cost. This is total, but this is the changing one, the variable cost. And make sure that you know how to evaluate this definite integral. Okay, good question. Okay, let's see another one. Okay, similar, but now we do have, instead of a function, we have a values from the table. The marginal cost, C prime Q in dollars per unit of producing Q units is given in the following table. And we do have the marginal cost values. If fixed cost is 10,000, estimate the total cost of producing 400 units. Okay, that means similar question, almost the same. I have to evaluate, let me write total cost, okay, will be defined as a fixed cost plus a total change, which will be the total variable cost from 0 to 400 units of the marginal cost function, dq. Okay, that means that's the formula that we have to work on. Okay, fixed cost again, and the total variable cost, total change in the function if the marginal cost is given. Okay, that we have to estimate this. And what we can do, you remember we had like the left-hand side and the right-hand side method. I can read, but maybe I can draw this, because then I think maybe doesn't work for all of us, but I think it's just a little bit easier to plot these points on the graph. and then I nicely see my rectangles, I nicely see the left, the right-hand side, yeah, instead of like purely memorizing. Okay, that's what we have. We do have the quantity. We have a quantity 100, and the marginal cost for 100 is, hang on, let's start with 0. 0, the marginal cost is 25. What values we have? 45, 35. Okay, let me put 25 here. Yeah. For 100, we have actually 20. Right, 20. For 200, we have 18. Oh, a little bit too tight, but it's okay. 18. Okay. And then for 300, we have 22. Oh, let me make this 22 and 25. 25 for 0 will be here. And 22 for 100 was okay, right? No, 25. Okay, 25 for, no, 20. That was correct. Okay, one more time. For 0 is 25. For 100, we do have the value 20. For 200, we have 18. Okay, I am at the 18 level. 300 is 22, and we need 400. 400 is 28. Okay, I can keep working. 28. And actually, I will put 500 also. 500 will be 35, a little bit taller, okay? And we also have 45 for 600. Okay, that's my quantity, and that's the marginal cost. Okay, that we can see the function, my dots, except this one. And I use different color, 25, 20. My green dots, yeah, they are like, we have decreasing values and then increasing. Okay, but now I have to estimate the areas. That means having these sub-intervals, I will create the left and the right-hand side. That means let's start with, I can use the green, the left-hand side. That means we remember 0 and 100, 0 is on the left-hand side. That means the value for 0 will give me the height. Between 100 and 200, 100 is on the left. The area of this. 200, 300, 200 is on the left. Between 3 and 400, 300 will give me the height. Okay, perfect. That means just the areas of these green rectangles will give me the estimate, like the approximation of the definite integral, but using the left-hand side. That's what we have, delta x. Do you remember? Delta x is simply, that distance. Okay, I will not call delta x for you because we have, just this width. We will call 100, okay? Because we can see from 0 to 100. That means the base of this rectangle is 100. 100 and times the value, 25. Okay, and then another 100 and times the value for 100, 20. 100 and times the value for 200 was 18. And another one, value for 300 was 22. Okay, so now I have to add all of them. 25, 20, 18, and 22. 18 and 22 is 40, 40 and 45, 85. That means we do have 85 and 2 zeros, my comma, because it's times 100. Okay, 85, 100. Okay, that's the, and of course it's everything, it's in dollars because that's the total change in my cost. And that means that's the dollars. Okay, now let's use maybe blue and let's estimate the right-hand side. That means theoretically we can add 10,000 plus this. And this is one of them, but let's try, maybe we can take the average of both of them. That means the right-hand side will be different. Let's do again. Looking at the interval from 0 to 100, 100 is on the right-hand side. That means this, the blue rectangle, will give me the value for that area. 100 and 200, 200 is on the left, on the right-hand side. This rectangle, 200 and 300, 300 will give me the height of this one, and 400, it's on the right-hand side, will give me the height. Okay, that's we have 100 times the value for 100, 20. 100 times, 100 is the base, yeah, we know that. The blue one has the value for 218. Now the value for 300 is 22, and the value for 400 is 28. Okay, that's what we have. We have 28 plus 22, which will be 50. 50, my phone is on. 50 and 70 and 18, 88. 88 and 2 zeros, okay? And of course in dollars. Okay, that's when they almost the same, but we can try to take the average. 850 plus, 8,000. No, 8,500. 8,500 plus 8,800. Add together and divide by 2. It's 800 and 500. It's 13 divided by 2, 650. That we will have $800 and $650. Yeah, again, I'm trying to do without the calculator. And that's what we can say. We can say that the total cost, total cost is simply my fixed cost plus that's what I just calculated. Okay, and this will be 18,650, and of course dollars. Okay, that means this is the fixed cost and this is the variable cost. Okay, that means hopefully my rectangles are helpful for you. If you can read the values right away from the table and you can do this green line and the blue line, that's also fine. But you'd like to have this graphical explanation, like how we're really getting these values. And it's just the areas of the rectangle. Okay. What we have another question. Okay, that we do have some initial values and we have to use the fundamental theorem of calculus. That means, let's see. The marginal cost C prime Q in dollars per unit of producing Q units is given by the following table. And actually, is this the same table? It is the same table, yeah? Okay. If the cost of producing 200 units is 16,000, estimate the cost of producing 400 units. Okay, that's me now what I will do. Now, I will write the fundamental theorem of calculus. The difference between the cost of 400 and 200 is defined as a definite integral from 200 to 400 of the marginal cost. Okay? And we're looking for the cost of 400. I will simply add this to both sides. I have to rewrite my integral. That means I am adding this. This will be positive, and I will copy for you the integral. C prime at Q dq. Okay, that means the cost of producing 400. We simply have to put 16 because that's given. And we have to evaluate this integral. And again, we can try to do the left and the right-hand side. We can use the the rectangles from the previous one. Okay, that's me. Let's see. Because we will need only from 200 the cost between 200 units and 400 units. That means let's see. Hopefully we can, between 200 We can see this, and 400. That means can you tell me, maybe you can tell me something because I'm not asking many questions. Let's use the blue rectangles and then the green rectangles, and we will add them together, divide by 2, we'll take the average. Okay, that means the blue rectangles will give me the area 100 times 22, 100 times 28. Okay, that means, and blue was the right. Okay, that means this one, yeah, right-hand side will give me just 22 and 28, correct? We know where the values come from, which is 5,000. Excellent. And now I can also estimate this using the left-hand side. Can you tell me the left-hand side, the green? This one is 100 times, what's the value for 200? 18, right? That means 100 times 18, 100 times 22. Do you agree with this one? This one will be 18 and 22. Thank you. Please watch me because I'm not, I think I know what I'm doing, but we never know when is the mistake. And this one is 4,000. Okay, that means we have the estimate. We can add 5,000, we can add 4,000, or we can add the average. What's the average of 5,000 and 4,000? Can you tell me? Of course, 4,000. I'm just trying to use nicely the colors for you, which this will be 450. Okay, I mean 4,500. Right? That's what I substitute. Okay, that means the cost of producing 400 units, it's simply $20,500. Let me put dollars. Thus we can see how nicely we can use the fundamental theorem of calculus. Okay, make sure that you follow this at your quiz. Okay. What we have? Oh, okay. Let's try. This is similar question, but no values from the function. We have a function. We have actually the formula. Okay. Suppose that the marginal cost for manufacturing company are increasing as a function of the quantity produced is defined this way. C prime Q is 6Q plus 12, where Q is the quantity produced and the units of C prime are dollars per unit. Of course, dollars per unit is the rate of change. If C at 0 is 1,400, calculate the total cost of manufacturing 100 units. Okay, that we don't have any information about the fixed cost. That means we just looking at the values between 0 and 100. That means 100 units. Calculate the total cost. That means the total cost will be defined. The total cost at 100 minus the total cost at 0 is defined as a definite integral between 0 and 100 of the marginal cost function. Okay, that means the total cost at 100 will be the total cost at 0, which is this one, plus the integral from 0 to 100, and I can put the formula 6Q plus 12 in this case. One more step, few more, but for my equation. This is 14, and this one I have to evaluate. And we know that this is the nice linear function. Linear, my pronunciation is weird. 6Q plus 12. 12 is the vertical or I can say the y-intercept, because normally the vertical line is defined as a y. That means 12, and the positive slope, 6. That means I can draw like that. 12, make sure that we know that value, and just this. And we're just looking at the interval between 0 and 100. Again, my units are a little bit weird, but the labels are correct. Okay, the same situation. That definite integral is the area under the curve. I will divide by the rectangle and the triangle. That means the rectangle will give me the area base times height, 100 times 12. The triangle, it's 1/2 times base, and again, I need this value. Do you think you can tell me what is the question mark? Who can tell me what's the value of that line, which is this function, at 100? No? We can simply take this formula, okay, and substitute 100. Can you do it for me? 6 times 100 now. I hope, are you there, right? We do have actually lots of participants today. Thank you, Charlene. 612. Okay, yes, Craig, thank you. I know it was an obvious question, but I'm just checking if you are there. Okay, that means this is, okay, ready? I have another question. If this value is 612, what is actually the height of my triangle? Oh, I want everybody to type for me. Oh, no, wait. Oh, okay, we have to. Okay, let's see. The whole, this is 612. This is 12. That means, Ralph, yes. Okay, no, it's okay. I know it's easy to add, yeah. We have to just 12 and then 600, 612. That means this is actually 600. Okay, yeah, don't make this mistake. Okay, that means my triangle is 1/2 times 100 times 600. Let's put this together. That means the rectangle, I can actually plus the triangle. No. Nice, right? That means the area of the rectangle is 100 times 12. The area of the triangle, that's my triangle actually, by the way. I don't know if we can nicely see. Okay. The triangle is 1/2 times 100 times 600. Okay, again, I think I don't have the calculator. That's easy. That's 12 and 2 zeros. And this one will be 1/2 of 6 is 3. That means it's 300 and another 2 zeros. Makes sense? Because always when we multiply by 100, we're adding 2 zeros. When we're multiplying by 1,000, we're adding 3 zeros, and so on. Okay? It means the total cost is 26 and 30. That means 32,600. Please check. 26, yes, thank you. Because sometimes the zeros, and then it's 30 plus 2, 32, okay? That means that's the total cost of producing 100 units. Again, I use the fundamental theorem of calculus. Definite integral through the area. Okay, yeah, of course, this is dollars, right? I can put, that's dollars. Okay. I will skip this one. Oh, and that's probably almost the same question that we did. We're really practicing the fundamental theorem of calculus, but no, everything is given. Almost everything is given. We don't really have like the application. Yeah, we have just the mathematical values. Okay, suppose that k at 0 is 10, and k prime at x is 2x minus 6. Calculate k at 4. That's when we can probably guess that the total change in the function that we're looking is between 0 and 4. That means the total change between 4 units and 0 units is defined as a definite integral between 0 and 4 of the rate of change, k prime. That means the value at 4, it will be value at 0 plus the integral between 0 and 4 of 2x minus 6. Okay, really easy. This is 10, and this one we have to do it, and we know how to do it, right? This function has, negative. We can see the y-intercept, the vertical intercept is negative 6, and the slope is positive. I can draw maybe like that. That's, of course, the graph of this. And I'm looking at I'm looking at the net area. Yes, we remember from last week, if the area is below the x-axis, everything is negative because the actual value is involved. That means 0 and 0 and from 0 to 4. Okay. We can probably find this number, the x-intercept. If I take my function 2x minus 6, it must be 0. That means this is 0 if x is 3. That means this value is 3. Okay, that means my scale is a little bit weird, but that's okay. Okay, that means now we're looking for the net area because that's the definite integral of that part, which will be negative, and this one. Okay, this one is above, this one will be positive, but please remember this will be negative. Okay, that means what we have. Let's find out, where can I write? Maybe here. This is a triangle, which means the area is 1/2 times base. I am assuming that the base is 3 and the height is 6, but everything will be negative because it's below the x-axis. Negative 9, I believe this is negative 9, and this one is also a triangle, 1/2 times base, distance from 3 to 4 is 1, and now I need this value. Let me move this a little bit. Oh, no, because I want this value. Actually, I can write here, 1/2 times 3 times 6, but it's negative. Negative 9, that's this one. And I need this value. Who can tell me again the question mark? Because that's what you have to figure out, right? Because I need the area of this triangle, which will be 1/2 times base times height. That means this is my height. Who can tell me this? I need height. I need this value. Question mark will be exactly the same because we're touching the x-axis. Okay. No, who can figure out that question mark? Because without this, you will not get this question. What we can do? Oh, now you can try. How can we get this? This is just the point on the line, okay? And this is my line, right? That means, and it's the value for 4. Can you just substitute 4? K prime at 4. Yes, it's I was trying to do is 2 times 4 minus 6, which is 8 minus 6 is 2. Thank you. But make sure that you know how to get that 2, because without this, we're really getting the wrong answer. I mean, no answer. Okay, that means I'm coming back to my triangle. 1/2 times base times height, which this will give me 1. Okay, that means this triangle has the area 1. That means the circle 1 are the areas. We have to add them together. Negative 9 and 1. Okay. 1 is from the top, negative 1 is from the bottom. We can see it should be a little bit, my graph is not really representing the values, but again, the labels are correct. Okay, that means that will be the final answer. 10 minus 9 plus 1. k at 4 is, I believe, 2. It's just coincident that that 2 and this 2 is the same. Yeah, of course, that's nothing. They don't have really connections. Okay, but again, fundamental theorem of calculus. Okay, and what I have another one, which is, okay, a little bit different, but I can leave this one for you. I can tell you that the value for k at 2 is -17. Okay, try to solve it on your own. It's exactly the same question like this one. Okay, that means try to make it -17. And I will skip this question. I have another one, but you have solution. Okay. That means now we have just 2 things actually. Okay? That means this one is the average value, which we have to just know the formula and apply. And I also have another, like the fundamental theorem of calculus, but part 1. Hopefully we also remember that I can show. Okay, that means what we may also try to compute the average value. And the average value, it's kind of like the area under the curve of the function, and we have to divide or multiply by the reciprocal by b minus a. And b minus a, it's simply the amount of units between a and b, right? Like we can see if this is 2 and 7, that's what I think I said today, the difference will be 5. That means that will be 5, for example. It's kind of like computing the average. We like adding everything together and dividing by number of data points. That means something similar. Just the average value of this. The area under the curve and dividing by the amount of units. Yeah, that means let's see. Simple questions. Yeah, we will have really simple question. What is the average value of the function f on the interval between 0 and 6? And that means this is just the average function of the blue curve between 0 and 6. And we know that the average value, it's simply defined as an integral from 0 to 6 of this function. And we will divide by 6 minus 0, which of course is 6. I mean, that's the formula for the average value. Okay, 1/6 times my definite integral has to be computed as an area under the curve. Do you remember, like we can maybe start counting the squares. Each square is 1 by 1. That means let's see how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and this one will give me 14, 15, this one, 16, 17, 18, 19, 20. Oh, okay. That means I have 20. We can see it's all of them are that's the area under the curve. That means I do have 20 times 1 because the base, it's simply 1. I mean, I can even say 1 by 1, just in case if this will be not 1, right? I know that 1 is not affecting because base times height, 1 times 1, it's still 1, but please remember just in case if this will be different. Okay, this is simply 20 over 6, or I can say 10 over 3, I can say 3 and 1/3, or if you prefer, we can do this way, okay? But probably this answer is fine. Okay, that means just 3.3. That's the average value of the, how can I say, total change in the function f. Yeah, of course, it's the average value. Okay, let's try one more. Oh no, are we gonna count? Shall we do this? Because this one has the curve that we have to kind of like, but it's the same thing. Let's just set up. Maybe you can start counting the area under the curve, and I will write for you the formula, average value. 5 minus 0. Of course, I'm taking these values. And the integral from 0 to 5 of the function f of x dx. This means the average value will be 1/5 and the area under the curve. Again, each square is 1 by 1. That means at least we have to just count them together. Okay, 1, 2. Do you have 25? Okay. Okay, shall I can say 25, and I can say 1 by 1. That means it's just 25 over 5. That's actually a nice number, 5. Let me do the approximation. Shall we count 4, 5, 6, 7, 8, 9, 10, 11. Probably I'm not going to get 25, or maybe 14, 15. And then I have 16 here, 17, 18, 19, 20, 21. 21, and let's say 22 with this one. Let's say 23 with this one. Maybe 24 with this one. Yeah, because we're missing, but we have. And then, yes, I can say 25 with all of them together. Approximately 25, 20, but I think 25 is a good number. And don't worry, if this will be a multiple choice question, I'm sure we're not gonna give you like the option, 25, 26, 27. No, we will really spread the values. Yeah, that because it's not, that's not the point. We just want you to approximate this correctly. Okay, and then I will skip this one because it's the same idea. Okay, and now I have the last two questions. Because also the fundamental theorem of calculus part 2, it's telling me, and I have written here. That means what we have, let's say, if I can write one more time, if the function g of x is defined as an integral from a to x, I know looks a little bit weird, f of t dt, because x is the upper limit of integration, then if I would like to find the derivative of this function, derivative of this, because we kind of like learn that integration and differentiation is the opposite to each other. That means taking a derivative of this, we kind of like canceling they cancel each other. Yeah, that means integration and differentiation is gone. Or maybe I can use better notation. Okay. Oh, actually, I can write it down. That means taking the derivative, I will take the derivative with respect to x of this integral. With respect to t, because we will substitute. That means that's what I was gonna show you, that differentiation and integration can cancel each other. And we don't even have to do much. We can, the only thing that will stay will be the function that we were integrating. But we always have to substitute x because it is in terms of x. That means this is, it's like weird because looks so simple and so like, no, we don't even like think, oh, why are we even doing this? But it's so important and it's so like, oh, it's the crucial like concept of calculus, of course. But please remember that because that's the fundamental theorem of calculus, the other part. If we're trying to differentiate an integral, we don't have to do anything. It's just, oh, that's my name. It's just this function. All right, that's me. Let's see what we do, what we have. G of x is defined as an integral from 5 to x, e to the t dt. And we have to find the derivative of this. Right? That means derivative with respect to x, it will be the derivative of this integral, e to the t dt. And we know that the differentiation and integration, they cancel each other. That means what's left, e, but instead of t, we always have to put x, the upper limit. Okay, always. Also, please note that the lower limit of integration, 0, 5, could be any number but the fixed, the constant number. No x, no other like variables. 0, 1, 2, 3, negative, 5. This is not really affecting that at the moment, of course. Okay, but we can see the answer is just this function, just simply this function, and instead of t, x, the upper limit, okay? Because they cancel each other. Okay, and I have another one. That means what's the answer to this question? What is derivative of g prime of x? Can you type for me? Yeah, it's just, doesn't really matter how the function is defined. It's just this function. Okay, that means it's so easy and nice question to differentiate from 5 to x, 5t to the 6 dt. The differentiation and integration, they cancel each other. We will only have this, but please remember, please substitute instead the same, copy the same formula, copy the integrand, but instead of t, put x, the upper limit. Okay, that's it. Even if it looks so, how can I say, trivial, so obvious, it's important. And we will see, because we will use this. In chapter 6, we will actually try to develop more like systematic ways to integrate a function. Okay? We will get some formulas. The same like with the differentiation, we did have the estimation at the beginning, like the slope of the curve, but later we get nice formulas. The same will apply for integration. Okay, thank you very much. That's everything for today.